In this video, we are going to discuss nucleophilic substitution Sn1. Because Sn1 is competing with elimination E1, we are going to talk about both Sn1 and E1. As an example, let's take a look at this reaction and let's go through the steps of the mechanism. This carbon-bromine bond is a polar bond, and there is a partial positive charge on a carbon, delta plus, and partial negative charge, delta minus, on a bromine. Because of that, at some point, bromine can depart, and that is our leaving group, and by doing so, an intermediate is formed. This intermediate has a positive charge on carbon, middle carbon, and is called a carbocation intermediate. It is important to emphasize the order of stability of carbocations. Tertiary carbocation is more stable than secondary, more stable than primary, which is in turn more stable than methyl carbocation. In the next step of the process, a weak nucleophile methanol comes in. Lone pair of the oxygen atom acts as a nucleophile and attacks the positive charge on a carbon, which is the electrophile. After the nucleophilic attack, we have a second intermediate where oxygen atom bears a positive charge as a result of sharing the electron pair with carbon. Third, and the last step of the mechanism, is a proton transfer. Another molecule of methanol could come in and pick up an extra proton from this intermediate, and as a result, we end up with a neutral molecule, which is our final product. Very important. Carbocation formation is the slow step of the process, which means in this case the first step of the reaction. That is the rate determining step, RDS. Second and third are the fast steps of the process. Because of this, the rate law equals constant times concentration of alkyl halide, and if you notice, only alkyl halide participates in the slow step of the reaction, and that is why this reaction is called unimolecular nucleophilic substitution Sn1. Because Sn1 and E1 go hand in hand, let's do the mechanism for E1 as well. After the carbocation intermediate is formed, methanol can act as a base as well and come in and deprotonate on a beta position. After methanol removes the beta hydrogen, that bond shifts between alpha and beta to form a double bond. This process is called elimination E1 because again only alkyl halide is participating in a slow step of the process. On the energy diagram we can see 3 steps and 3 hills. The first step has significant energy of activation, and that is the rate determining step. Second and third are the fast steps of the reaction. Also very important is that intermediates are higher in energy than both reactant and the product. Transition state is energy maximum, labeled with TS double dagger, and is always the highest in energy level, higher than intermediates, reactant, and the product. Now we can talk about the stereochemistry of Sn1 reaction. If you start with a chiral reactant and perform Sn1 reaction, you would lose any chiral information and end up with a racemic mixture. This result is the consequence of the mechanism. During Sn1 reaction, the intermediate that gets formed is a carbocation, and as we know, carbocations have planar geometry and they are sp2 hybridized. Meaning, nucleophile attack can happen with equal possibility from either face, left or right, resulting in the pair of enantiomers. And as we said before, equal amounts, 50% of R enantiomer and 50% of S enantiomer in a mixture, is called a racemic mixture. Overall, that racemic mixture shows specific rotation alpha equals 0. In conclusion, good candidate for Sn1 reaction is a tertiary alkyl halide. Sn1 can happen with a secondary one, but never with a primary alkyl halide. Please recall the stability of carbocations. It is very important to remember that primary carbocations do not exist. Weak nucleophiles and weak bases are also good candidates for Sn1, such as water or alcohols. Sn1 is usually performed in water or alcohol as a solvent, so those have a double role. Nucleophile or a base is also a solvent for this reaction. Leaving group ability is the same as what we previously said when we talked about Sn2. Iodide is a better leaving group than bromide, better than chloride, and finally fluoride is the worst leaving group.